All right, so chapter 9, number 60. 960. Use the data from the tables of ionization energies and electron affinities on page 343 and 348 to calculate the energy changes for the following reactions. So we have sodium gas coming together with chlorine gas to form sodium chloride. Solid gas. Oh, no. Sorry. First, sodium ion to chloride ion. Sodium ion, gaseous, to form, and chloride ion, gaseous. All right, so that's the first step. And the next step is sodium gas, or not the next step, but this other reaction is sodium gas, two chlorine gases coming together to form sodium ions, gaseous, and two chloride ions, gaseous. All right, so use the data from the tables of ionization energies on pages 343 and 348. Okay, so we have 343. We can find the successive ionization energies in kilojoules per mole for hydrogen through magnesium. So we look for sodium, and we see that this ionization energy here is 496 kilojoules. All right, 496 kilojoules to add an electron. All right, no. So this is not a positive. So to remove an electron, 496 kilojoules of energy. So there's 496 kilojoules of energies to remove an electron here. For the chloride ion, that's going to be on page 348. For a chloride ion, we see that if we give it an electron, we receive 348 kilojoules per mole. 348 kilojoules per mole. So that is negative 348 kilojoules per mole. All right? So this reaction, for this reaction to occur, we expend 496 to take an electron from sodium. We receive a 348 when we give an electron to chlorine. So the difference here, let me get my calculator so I can have it available to me. So we got 496 plus a negative 348, and this is a positive 148 kilojoules. So the resulting, energy released upon the formation of these, the salt between the sodium ion and the chloride ion, which is called the, the lattice energy. The lattice energy, when sodium ions and chloride ions come together to form that lattice, has to be more than 148 kilojoules so that this reaction, because we know this reaction occurs, right? All right, now the other reaction where we have sodium gas going with two chloride ions. Well, it's becoming a sodium 2+. That's what's occurring here. We have a sodium 2+, right? So when we want to perform this reaction here, we have to look at the energy required to, let's see, where are we at? Back on page 343. 343, we look at our sodium, and we see that the second energy to remove the second electron is 4,563 kilojoules. So the first electron is 496. The second one is 4,563. So this is going to be the energy required to remove both of those electrons, which is 4,563 plus 496, 5,059 kilojoules to remove electrons, two electrons from sodium. And then the chlorine ion, if we're going to do two chloride ions, then we're going to have a negative 348 times 2. All right, and we're going to add those two together. So we have 5,059 minus 348, and then minus 348 again. And the result here is going to be 4,363 kilojoules per mole, right? So this is what the lattice energy would have to be for us to form NaCl2. Okay, and this is what the lattice energy would have to be overcome to form sodium chloride. So if we take this and divide it by 148, we see that it's almost 30 times as large, 29.5 times as large. So we have to have about 30 times more lattice energy released to form this compound here. All right. So 962. Explain what happens to the electron configurations of magnesium and bromine when they react to form magnesium bromide. All right. The electron configuration. So if we draw the electron configuration for magnesium, have the periodic table here. It's 1s2, 2s2, 2p6, 3s2. There's magnesium. And bromine's electron configuration. We'll just start with argon, because bromine's a little bit longer, too long. Argon, and then 4s2, 3d10, 4p5. 4p5. So when magnesium and bromine are going to come together, that means magnesium is going to form a +2 ion, and bromine is going to form a minus ion. So the electron configuration, if this is going to be a +2, we're going to have to lose these two 3s2 electrons. We knew we had to lose the 3s because they were the highest energy, right? The highest N value. And here we're going to gain an electron, so instead of 4p5, it's going to become 4p6, and that'll be the electron configuration of the bromine minus ion. So explain what happens to the electron configurations of magnesium and bromine. That's what happens. Double check that, make sure they're not looking for something else. 962, magnesium loses 2 electrons, bromine gains an electron. All right. To keep the overall charge unit stable, we need 2 bromines, right? What are the electron configurations of the lead +2 and the lead +4 ion? All right, so we have our lead ion here at 82 electrons, 82 protons. The lead atom, there's the lead atom, and we're going to make the +2 and then the +4. All right, so to draw the electron configuration first for lead, we'll start off with xenon. Okay, we go from the xenon, we get 6s2. After our 6s2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 Fs, right? So 4F14, and then we have our 3, 4, 5 D10s, okay? And then we have, so we have our 6s2s already, 5 D10s, and then we have 5p2. All right, so that is our lead atom. And the Pb+2 ion and the Pb+4 ion. Those are the questions, right? What would be the electron configuration? Well, for the Pb+2 ion, we would lose 2 electrons. Which 2 electrons would we lose? Oh wait, this isn't 5p, this is 6p. 6p2. Right? Yeah, 6p2. All right, so which 2 electrons would we lose? Well, to determine which electrons to lose, we look for the ones with the highest N value, which is the 6, the 4, the 5, the 6 here, right? So the N value, the highest N value are these 2 6s. And then we go to the, if there's more than one orbital or subshell, then we go to the one that has the higher L value, which is in terms of SPD or F, which is higher energetically than SPD or F. So P is higher. So those are the first 2 electrons we're going to lose. So if we lose those 2 electrons, then we're going to be left with the xenon core, 6s2, 4f14, 5d10. So there's one ion. And then the second ion would be losing the other 2 electrons in the sixth shell, leaving with this 4F14 and 5D10. Now, it doesn't matter the order in which you put these. So the 6S could be here and the 6P could be over here. It doesn't matter the order in which you put these. You just want to make sure that you don't forget that you have some 6S's here, right? If you draw them that way. Okay, 664. Let's double check that one real quick. 664, the P's first and then this S's, yeah. Okay, 666. Oh, 966. 966, good. Write the abbreviated electron configuration of the manganese plus 3 ion. How many unpaired electrons does it have? So we have the manganese plus 3 ions, so we're looking at 25 here. Abbreviated, we're going to start with, so let's just do the manganese first. We have argon, and then we have 4s2, and 3d what? 4s2, 3d1, 2, 3, 4, 5, 3d5. So this is the manganese ion, and the Mn plus 3 ion is going to be formed by the abbreviated electron configuration for the Mn plus 3 ion. So make sure we're doing that right. 1, 2, 3, 4, 5. Yeah. Argon, 4s2, 3d5. Manganese, correct? All right. So we're going to lose these electrons. Oh no, sorry, not those electrons. These electrons here. 4s, highest energy level there. So we're going to be left with argon, and then we're going to have the 3d, and we're going to lose one of those, so it's 3d4. So Mn plus 3 ion would be a 3d4. And then if we imagine that d orbital, or that d subshell, right, and the 5 different orbitals, and if we have to fill this with 4 electrons, 1, 2, 3, 4, then there's going to be those 4 lone pair, or 4 non-unpaired electrons. And how many unpaired electrons does the ion contain? So the answer has to be 4. All right? Let's double check that one. 966. Okay. 3d4 and 4 unpaired electrons. Great. Okay. 968. Write the Lewis symbols for the following atoms. Okay. 968. All right. The Lewis symbols for the following atoms. Okay. Silicon. Well, the big thing we have to do to draw Lewis symbols is just identify how many low valence electrons there are. Counting from, here's silicon right here, right? Counting from left to right. 1, 2, 3, 4. So silicon has 1, 2, 3, 4. And that's how we draw the Lewis structure, right? We put an electron on, we spread the electrons out as much as possible. If there's 8, then if there's more than 4, then we start pairing them up. But we don't put 2 on one side until all 4 sides have this side, right? Have an electron. So next, 468, we have antimony, Sb. It has 5 electrons, 5 valence electrons, outer shell electrons, 1, 2, 3, 4, 5. So that's for antimony. Barium has 2. 1, 2. That's good. It could be up here. Doesn't matter. Just 2 electrons though. Aluminum 3. 1, 2, 3. All right. Sulfur 6. 1, 2, 3, 4, 5, 6. Okay. So those are the Lewis symbols for those elements. All right, 968 to 970. The Lewis symbols, use Lewis symbols to diagram the reaction between calcium and bromine. All right, so for example, we have calcium going to and bromine coming together. Calcium has 1, 2 lone pair, or not, outer electrons, valence electrons. Bromine has 7, 1, 2, 3, 4, 5, 6, 7. So we're going to need 2 of these. So calcium is going to combine with 2 bromines, and the result is going to be the calcium ion is going to lose these 2 electrons and have a +2 charge, and this bromine here is going to have gain. So I'll make these X's, these X electrons, so that I'll show that 1, 2, 3, 4, 5, 6, 7, and now bromine picked up that extra electron, became a -1 charge, and then we had a different bromine over here, 1, 2, 3, 4, 5, 6, 7, pick up that other electron with the -1 charge. So this is the chemical reaction between these two, right? So these X's here represent the electrons for the calcium, these dots represent the electrons for bromine, and we needed 2 bromines to do that. Okay? Let's double check that one really quickly, 970. Make sure there's nothing else I can get. So, oh, we have more to go. Aluminum and oxygen, and potassium and sulfur. Aluminum and oxygen. So we have aluminum. It has 1, 2, 3. Oxygen has 1, 2, 3, 4, 5, 6. Again, aluminum is the 3rd column if we just count the S block and the P block, right? Then we can use those column numbers, or 1st, 2nd, and then the boron's column is 3rd, carbon's 4th, nitrogen 5th, oxygen 6th, fluorine 7th, helium 8th. And those columns, using that number system for those columns, will indicate how many valence electrons or outer shell electrons there are. And that's how many dots are going to be around the in the Lewis structure, right? So if aluminum is going to combine with oxygen, you know, it's easy to keep in mind that we already know this, that this is going to be Al2O3. So then we can draw our 3 oxygens and our 2 aluminums. 1, 2, 3, and I'll drop, maybe make these X's here so we can see where they go. And I saw in the back of the book they're drawing arrows, so that can help us, right? So the aluminum needs to lose all 3 of these electrons, right? And let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I had forgotten one there. So aluminum needs to lose all these electrons to some spot. So this electron will be down here, right? So you're going to get aluminum with a +3 charge, and that's the Lewis structure of an ion. That's how you do an ion. Oxygen with a -2 charge, and it has 1, 2, 3, 4, 5, 6, 7, 8, right? Got 2 electrons. We're drawing them as X's. You don't need to draw them as X's, but that just shows that they came from somewhere else. 1, 2, 3, 4, 5, 6. -2. And then we need another one. We can draw nearby here. 1, 2, 3, 4, 5, 6. And this is a -2 as well. All right, so this here would be the Lewis structure for an ionic compound. All right, we have one more, potassium and sulfur. So again, we know that this is going to be a K2S. So potassium ion has 1 electron. There's going to be 2 of them, 1 electron. Sulfur ion has 1, 2, 3, 4, 5, 6. Sulfur 1, 2, 3, 4, 5, 6. I'll draw these as X's so we can differentiate them. Whoops. Just 1 sulfur, right? There we go. So then the sulfur is going to have 1, 2, 3, 4, 5, 6, 7, 8. And it's going to have a -2 charge, and the potassiums are both going to have a +1 charge. So that is how we use the Lewis structure system to draw an ionic compound. All right, so number 972. we're supposed to calculate the charge that is on, what does it say? Use the table and data in table 9.3 to calculate the amount of charge on the oxygen and nitrogen in the nitrogen monoxide molecule. Expressed in electronic charge units, or electrons, E's. Which atom carries the positive charge? Okay, so to do this, on page 378 we have table 9.3. Okay, and table 9.3 tells us that the dipole moment in debye is 0.16. So 0.16 debye, right? And we see that 1 debye is equal to, you can see on this page, or just below the equation on page 378, equation 9.2, we see that 1 debye equals 3.34 times 10 to the minus 30 coulombs, all right? Coulomb meters. So we have 3.34 times 10 to the minus 30 coulomb meters for every 1 debye. Okay? And so now we're in coulomb meters, and this isn't centimeters, right? This is big C, coulomb meters. And if we multiply, or if we divide this by our distance, then we'll be in coulombs. And the distance is 115 picometers. 115 times 10 to the minus picometers is minus 12. So that's how many meters are there. And so now we'll be in coulombs, and we need to get to electrons. So our answer is in coulombs now, and 1 electron is 1.602 times 10 to the minus 19 coulombs. So we divide that by 1.602 times 10 to the minus 19th coulombs. That way coulombs will cancel out, meters will cancel out, and that's 1 electron there, right? So we'll be in electrons. Debye's cancel out. All right. So 0.16 times 3.34 times 10 to the minus 30 divided by 115 times 10 to the minus 12 divided by 1.602 times 10 to the minus 19. And I get 0.029 electrons. All right? So that is the answer. Or what was the question? Says which one has the positive charge? The positive charge is going to be, let's see, the more electronegative one, nitrogen is going to have the negative charge, so it's going to be positive charge on the carbon, the negative charge on the nitrogen. The nitrogen atom is positive. The nitrogen atom is positive? Oh, sorry, it's not nitrogen and carbon, it's nitrogen and oxygen. Right? Nitrogen and oxygen. And yes, oxygen is more electronegative. So oxygen is going to have the negative charge, and nitrogen is going to have the positive charge. Sorry about that, I forgot the compound. Okay, so that's right. Okay, good. Okay, 0.974. 0.974. Let's see, what is it? The dipole moment of HF is 1.83 debye. The bond length is 917. Calculate the amount of charge in electron charge units on the hydrogen and fluorine atoms in the HF molecule. So we have the hydrogen fluoride. The dipole moment is 1.83 debye, and the distance is 917 picometers. All right, so again, for every 1 debye, there's, what was it, coulomb meters. And here we're going to put 917 times 10 to the minus 12 meters. That's the length. So we'll get rid of meters here. Coulombs, what is the, turn back to that page, it was 1.602 times 10 to the minus 19. This is how many coulombs for every electron. And this value, how many coulombs were there per debye? 3.34 times 10 to the minus 30. Okay, so we have 1.83 times 3.34 times 10 to the minus 30 divided by 917 times 10 to the minus 12 divided by 1.602 times 10 to the minus 19. All right, so the answer is 0.0416 electrons. Okay, and did they ask anything else in that question there? Just the amount of charge, that's all they asked for. So 0.0416, let's see. 0.042. All right, good. 976. How much energy in joules is required to break the bond in one chlorine molecule? The bond energy of chlorine is 242.6 kilojoules per mole. So this is 976, right? 976. How much energy in joules is required to break the bond in one chlorine molecule? The bond energy for chlorine gas, Cl2, is 242.6 kilojoules per mole. That's per mole of that bond, right? And we're asking just one bond. So it's 242.6 kilojoules to break one mole of bond. And how much is it to break just one bond? Well, there's 6.02 times 10 to the 23rd bonds in let's see. This is 1 mole of bonds. So there's that many bonds in 1 mole of bonds. That's how much energy per mole of bonds. So we have to put our moles of bonds down. For every 1 mole of bonds, there's 6.02 times 10 to the 23rd bonds. So this will tell us how much energy for 1 bond, right? All right, so if we take 242.6 divided by 6.02 times 10 to the 23rd, then we're getting 4.03 times 10 to the minus 22, and that should be in kilojoules. All right, and did they ask how much energy in joules? So we take that and multiply it by, if that's kilojoules, so now we're in kilojoules. There's, in 1 kilojoule, there's 1,000 joules. So we multiply that by 1,000. So 4.03 times 10 to the minus 19. All right, so good. Got it, 478. 478. The reason there is a danger in exposure to high X-ray radiation, high energy radiation, ultraviolet or X-rays, is that the radiation can rupture chemical bonds. In some cases, cancer can be caused. Carbon-carbon single bond has a bond energy of approximately 348 kilojoules per mole. That's a carbon-carbon bond, right? What wavelength of light is required to provide sufficient energy to break the carbon-carbon bond? In which region of the electromagnetic spectrum is this wavelength located? So 348 kilojoules per mole. So that's per mole. We divide that by, well, let's see, this is kilojoules per 1 mole, and how much energy is required to break 1 bond, right? What is required to provide energy to break the carbon-carbon bond? Well, that makes it for every 1 mole of bonds, there's 6.02 times 10 to the 23rd bonds, right? So this will be how much energy is required to break 1 bond. So 348 divided by divided by 6.02 times 10 to the 23rd. And in kilojoules, we'll convert it to joules though, multiply by 1,000. It's 5.78 times 10 to the minus 19 joules of energy to break that bond. Now, we can go from energy is equal to Planck's constant times mu, and then speed of light equals mu times the wavelength, right? Frequency times the wavelength. All right, so this is our energy right here, right? So energy divided by h will equal the frequency. So divided by the Planck's constant, divided by Planck's constant. What was Planck's constant again? Planck's constant. Let's see, where is it? It's on page 312, 6.626 times 10 to the minus 34. .626 times 10 to the minus 34. So we take energy, divide it by Planck's constant, divided by 6.626 times 10 to the minus 34. I don't know what happened. Made a mistake here. Oh, there's the problem. So enter, bring it down there, go to push divide twice. So there we go. So the mu, the frequency, equals 8.72 times 10 to the 14th. All right, that's our frequency. If we take our speed of light, which is 3 times 10 to the 8th, divided by the frequency, all right, then that should be our wavelength. And I'm getting in meters, 3.44 times 10 to the minus 7 meters. All right, 3.44 times 10 to the minus 7 meters. And now we have to convert that to nanometers. Well, we want to find out what range it is. So for every 1 times 10 to the 9th meters, that's 1, oh no, there's, for every 1 meter, there's 1 times 10 to the 9th nanometers. So we multiply that by 1 times 10 to the 9th. And it's 343, or 344, about 344 nanometers. So, question 978, in which region of the electromagnetic, what wavelength? 344 nanometers. In which region of the electromagnetic spectrum is this wavelength located? That's the ultraviolet region, right? 978, let's see if we got that right. 344, ultraviolet region. Okay. 980, use the Lewis structure to diagram the formation of bromine gas. So we're using the Lewis structure now to diagram the formation of molecular compounds, right? 980. So we have bromine, 1, 2, 3, 4, 5, 6, 7, and bromine, 1, 2, 3, 4, 5, 6, 7. Now I filled it that way so we'll have empty spaces here. So what we see here is these electrons are going to come together and share a bond, and we're going to have bromine. Now this bond represents those 2 electrons that are coming together. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So those are the lone pair electrons around bromine. All right, so that's 980. Excellent. Oh, we have a B, I guess. Water. Use the Lewis structure to form the diagram the formation of water. So in water, oxygen, 1, 2, 3, 4, 5, 6. Hydrogen, 1. Hydrogen, 1. Electrons are going to share here. Electrons are going to share here. And the result is going to be a bond between the oxygen and the hydrogens, and then our lone pairs are still there. So that's for water. And the last one is NH3 from neutral atoms. Oh yes, so from neutral atoms. So NH3. So NH3, N, 1, 2, 3, 4, 5. And remember, we determine how many electrons there are based on the valence electrons. And we know how to find out how many valence electrons there are, right? Hydrogen, 1, hydrogen, 1, hydrogen, 1. Right? So we're going to form a bond here, and bond there. Okay? All right, 982. Use the octet rule to predict the formula of the simplest compound formed from hydrogen and selenium. Octet rule, well, selenium needs 2 more electrons, so it's going to be H2S or SEH2. Selenium hydride, SEH2. I guess is what we could call it. Selenium hydride. What's the other one? What are we on? 82. Arsenic and silicon. Arsenic and silicon. Arsenic, ASH3, right? Because arsenic needs 1, 2, 3 more. Silicon, 1, 2, 3, 4 more. Silicon H4, SiH4. Okay? 982. Anything else they're asking for? 982. Let's see what we did. H2S, H2SE, H3AS, and SiH4. So, I'm not sure why they put the hydrogens in front for the selenium and the arsenic and not for the silicon. It must be because these are known as acids, so it's more common to put them in front. But no big whoop. 984. Use the figure 9.9 to choose the atom in which the following bond that carries the partial positive charge. Figure 9.9. Let's see what figure 9.9 is. I mean, we don't need to for 980, we're 984. Nitrogen and sulfur, we know that nitrogen carries the negative charge. Iodine and silicon, iodine should carry it, it's more electronegative. Bromine and nitrogen, nitrogen should carry it. It's one of the big 3. Nitrogen, oxygen, and fluorine are the most electronegative. Carbon and chlorine, chlorine's going to be carrying it. What's the other questions? Silicon and oxygen, looking at the periodic table here just to make sure. Or silicon and iodine. I guess silicon and iodine, I'm not positive which one carries it because I'm not positive which one is more electronegative. So I guess that's what the chart's for there. Figure 9.9. Where is figure 9.9? Okay, so it's on page 380, and we see that silicon's 1.8 and iodine's 2.2. So iodine is going to hold the charge there. And we can see nitrogen and bromine, we know for that one. Carbon and chlorine, carbon's 2.5, chlorine's 2.9. Chlorine's going to have the charge there. So nitrogen is one of the big 3, so it's going to have in A, it's going to be on the nitrogen. In B, we saw that iodine was more electronegative, so it's going to be on the iodine, the negative charge. Oh, sorry, we're trying to find out which carries the positive charge. So in A, sulfur carries the positive charge. In B, silicon carries the positive charge. In C, bromine carries the positive charge. And in D, carbon carries the positive charge. All right. 986. Which of the bonds in problem 984 is the most polar? So 986, we try to find out which one is most polar. Basically, that has the largest disparity between the numbers, right? And we can use our figure there to verify for sure. What was nitrogen and bromine, nitrogen and sulfur? It's got to be nitrogen and sulfur, right? Because nitrogen is one of the big 3. Silicon and iodide are pretty close. Yeah, so nitrogen and sulfur is going to be the answer there. 984, 986, nitrogen and sulfur. All right, so 988, draw the Lewis structure for AsCl4+. AsCl4 with a positive charge. So the first thing we do here, when we're drawing our Lewis structures, we identify how many valency electrons are brought by everybody. So each chlorine brought 7 times 4, that's 28. Valence electrons, aspartame brought 765, so plus 5, so that's 28, 29, 30, 31, 32, 33. So there's 33, but we have a positive charge, so that removes 1 electron, so there's only 32 positive charge, okay? So there's 32 valence electrons that we have to distribute. We identify the central atom, In this case, it's going to be acetane because there's only one of them. We evenly distribute the chlorines around the outside of the acetane, 4 of them. Okay? And then we have to start adding valence electrons, or electrons, to this molecule. First, we fill the octet of the acetane, the central atom, whatever the central atom is, and it's full here. The next thing we do is we put, we count them up, 1, 2, 3, 4, 5, 6, 7, 8. So we've used up 8, so now we have 24 left over. And then we start filling up the outside electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24. All right, so we know that this whole thing is going to have a positive charge, right? So we can identify where the positive charge is here. You can look at acetane and find out it has 8 electrons, but how many electrons did it bring? Or no, sorry. It has 8 electrons around it, surrounding it, but immediately around it, it only has 1, 2, 3, 4 from these single bonds, and it brought 5 to the molecule, right? It had 5 valence electrons. So it had 5 valence electrons, and right now it has 4 right around it, so 5 minus 4, and that's 1, and that's going to be the +1 charge on that acetane. So there's where the +1 charge is. So that should be the molecule. Well, no, let's see. At this point, we can bring these chlorines in here and form a double bond, and that will give this 5 electrons here. All right, so we brought electrons in forming a double bond. Now we have 1, 2, 3, 4, 5, 6. Oh no, this is going to be, let's see, this is going to be a 7 minus 6. That's going to be a +1 there. Yeah, that's not what's going to want to happen. Acetane is going to hold on to that positive charge. Chlorine is going to hold on to the electrons because chlorine is more electronegative than acetane. All right, so that should be the answer for that one. 988A. Okay. 988B, ClO2 minus.